Hi, this is Professor Fernandez, and in this video we are going to talk about Module 1 of Lesson 15. The topic here for the video is scalar surface integrals over a parametrized surface. So we are going to start off with just talking about this definition, 15.1.1, and I'm just going to mention that this is effectively a generalization of the definition for surface area. So you'll notice that I'm assuming I have a smooth parameterization of a surface S, and I'm going to assume it's defined over a closed and bounded domain D to make everything nice, and of course F continuous on S. Then we can define the scalar surface integral of F over S as this quantity here. And in terms of the parameterization that we have up here, we can use our surface area element ds from the previous lesson being the norm of Ru cross Rv times dA. So the only difference here from what we did in the previous lesson, and I've summarized it over here in the notes, is that in the previous lesson, this is what we were working with, which is effectively the case when f equals 1. So the surface area definition is contained within this definition as a special case, but this one is a bit broader. So you might be interested in calculating the surface integral of a certain function other than the function 1, which will generate the surface area. Why would you want to do this, you might ask? Well, it shows up in other places and content down the road. For example, in the Stokes divergence theorems and other theorems related to those, where you calculate double integrals of functions that are not just 1, so you're not just calculating the surface area. The second thing I want to mention is that this is a concept up here, I'm looking here now, which should ring a bell a little bit. You know, if I remove the clutter here, if I were to just kind of get rid of one of these integral signs, there we go. And you know, because we're doing a double integral here, you might remember that we're integrating over an area, dA, and I got rid of this and made it just one variable. So I would get rid of one of these parameters, right, u and v. So you can see what's left is a single integral of a function where I have a one parameter parameterization times the norm of that derivative times dt, or du in this case. In other words, I'm back here. So in some sense, the surface integral, scalar surface integral definition we're looking at contains or reduces to the line integral definition that we were talking about in lesson 13. So once again, we're just building on the same concepts that we've been working on with now for a couple of lessons. So what I want to do next is actually show you how you calculate scalar surface integrals. Much of the work that we will do mirrors what we did in the previous lesson with calculating surface areas. Because again, all we're doing is we're allowing for the possibility that the integrand in our integrals is not 1, but it's some other function. Okay, so this first example says, suppose S is the unit sphere, x squared plus y squared plus z squared is 1, and then evaluate this scalar surface integral. So the first thing we have to do is we have to parameterize our surface. We're not given that parameterization, we're just given the actual surface itself. So when you're going to parameterize a surface, you have a choice of how to parameterize it. I'm going to talk through very quickly some choices here. The most natural choice would be to go with x and y as your parameters, because then the parameterization is x, y, and then f of x, y, where we're thinking here of z equals f of x, y. We could try that for this example, and we could solve for z here, and we would get something like this. The problem is that I technically need a plus or minus here. If I just choose the positive square root, I'm only looking at the upper hemisphere of the sphere. Then I would have to go back and somehow incorporate the negative square root to get the other half of the sphere. So while this is a natural parameterization, I don't recommend it for this problem. That's okay, because we have a choice, so we can go to another parameterization. We are dealing with a sphere, and we've learned about spherical coordinates. And you might remember that in spherical coordinates, x squared plus y squared plus z squared is rho squared. and therefore that the equation of this unit sphere in spherical coordinates would just be rho equals 1. That's pretty nice. And we have all sorts of formulas for x, y, and z in terms of rho, theta, and phi in spherical coordinates. So for all those reasons, I'm trying very hard to convince you that parametrizing this surface in terms of spherical coordinates is the way to go. So that's what we're going to do. So we're going to choose r of theta, phi, and actually I'm just going to write r of phi theta. This is how I tend to think of spherical coordinates. Rho first, then phi, and then theta. And then I'm going to write down my conversion equations for x, y, and z in terms of spherical coordinates. Remember, x is rho sine phi cosine theta. Rho here is 1, so I just get x is sine phi cosine theta. Y used to be rho sine phi sine theta. Rho was 1 again, so just sine phi sine theta. And then z is rho cosine phi in spherical coordinates. Rho is 1, so I just get z is cosine phi. Great, so this is my parameterization, and then I have two parameters, theta and phi. I am sweeping out the entire sphere. So remember, phi goes from the positive z-axis all the way down to the negative z-axis. That's what it's going to do here. Phi goes from 0 to pi to get the whole sphere, that slice there. And then theta goes from 0 to 2 pi to then sweep out all the way around the entire sphere. So I have my parameterization, I have my bounds, and now I'm just going to go back up and go to my definition and effectively do what we did before in the previous lesson to find the surface area elements and then multiply it by the integrand expressed in terms of the parameterization and then integrate it. So a few steps to follow, but nothing too different from what we've done before. I'm going to eliminate this clutter here. Okay, so to find that surface area element, I am going to need the derivatives of r. So in this case, it's r sub theta and r sub phi. So let's do r sub phi first. That is the derivative of this with respect to phi. So I get cosine, partial derivative, cosine phi, cosine theta. And then I get cosine phi sine theta. And then I get minus sine phi. And then I go back and I find the derivative of r with respect to theta. Once again, looking up here, partial derivatives, I get minus sine phi sine theta. I get sine phi cosine theta. And then there's no theta here. So that derivative with respect to theta is 0. Great. And then next step is to calculate r phi cross r theta, and then to find the norm of that. I am going to save you all of those steps. Again, now we're reviewing stuff we've done many times before, calculating the cross product of two vectors and then finding norms. So I'm going to save you those new steps to focus on the new stuff in this lesson and tell you that the outcome is sine of phi. Okay, so now I have my norm and I have my integrand. So now the next step is to express my integrand in terms of this parameterization that I've chosen and integrate over the region D, which we will figure out soon what it is. Great, so I'm going to make some more space for myself down here. Okay, so my integrand is x squared, and I know that x is sine phi cosine theta. So my surface area, my surface integral turns into double integral over d, we'll figure out what d is in a moment, of x squared. X is sine phi cosine theta squared. And then I just figured out the norm of RU cross RV in this case, and that was sine phi. And then my parameters are theta and phi. So, theta and phi, but I'm going to write it as d theta, d phi, d phi, d theta. Excuse me, and then so now I want to find the bounds for my region D. If you have gone this far, where you have figured out what the bounds are in the parameterization to begin with, which is what we did here, then it's really easy to figure out what your bounds are for the integral, right? We've already done the work. Phi goes from 0 to pi, and theta goes from 0 to 2 pi. Another way you could have done this is just to have figured out the parameterization first, and then done all the calculations that we did. Find RU cross RV, take the norm, express the integrand in terms of your parameterization, and then at the end of the day, go back and try to relate your parameterization to the surface that you're given. From that, which is what we did in the beginning over here, where I erased it, but I drew the sphere. From doing that is where you get the bounds for your parameters that then make their way into the integral. So at this point, we've set up a double integral, and I'm just going to simplify it a little bit and indicate some tips for how you might evaluate this, favoring instead for us to spend more time with the new concepts, given that this is just another double integral, which I'm sure that we can do. Okay, so what would I do here? Well, the first thing I want to mention is that one of these integrals, or I should say the integrand, is the form of a product of a function of theta and a function of phi. So this goes back to one of the properties we had talked about. When this is true, I can split up the double integral into the product of the integral of just one of these functions integrated over its respective domain times the integral of the other one of these functions of only the other variable integrated over its respective domain. So that's a nice property of integration. Why did I want to do that? Because now you see that we have reduced this problem to calculating two integrals, single variable integrals, right? And these are two particular single variable integrals which you may have seen in previous courses, for example, Calculus 2. I do want to talk through how to calculate this really quickly, each of these integrals. It's more of a reminder from stuff you have probably already seen, but maybe haven't seen it put together in this way. Because again, when we calculate double integrals and dealing with sines and cosines, there's lots of trig identities you might want to end up using. So I'm going to call this integral 1 and then integral 2. For integral 1, would we do this? Well, we'd use the fact that cosine squared theta is 1 plus cosine of 2 theta all divided by 2. If I do that, then integrating cosine squared is like integrating this function. And this 1/2 is going to integrate to theta, and then this integral of cosine 2 theta I can do with a u substitution. This will end up being sine of 2 theta divided by 2. So that's nice. So I can actually do integral number 1 without too much worry. For integral number 2, you might be worrying, what about that sine cubed? I don't have a trig identity for sine cubed. And I would say, yes, sort of. Sine cubed we can write as sine squared times sine. And we do have a trig identity for sine squared. Actually, we have a few trig identity for sine squared. You could go the route of 1 minus cosine of 2 theta, but then you have these frequencies that are mismatched. So I would not go that route. Instead, I would go the route of 1 minus cosine squared phi times sine phi, d phi. Because then if you write this out, you're integrating sine phi, which we can do, and then over here, you're integrating sine phi times cosine squared phi. And although that seems somewhat convoluted and complicated, if u is cosine phi, du is minus sine phi. So this integral will end up being a u substitution, whereas this integral is one of the standard integrals. So that, again, will enable us to do this number 2 integral also. After doing those two integrals, you get a number from here, you get a number from there. Multiply these two numbers as you can check, you will get 4 pi over 3. As we talked about before with surface area, you can interpret surface area as an actual area because you're integrating the function 1. That's the integrand, right? Going back to here. There's a f of x, y, z equals 1 there. However, in the case of surface integrals, there's no easy interpretation to do here. So I can't tell you that this 4 pi over 3 represents a surface area. It doesn't, for example. But again, this is yet one more instance where we can calculate these quantities we don't really have a nice real-world interpretation of them in all contexts, and that's okay. Like I said, later on in the course, we can relate these quantities to things that do have nice real-world interpretations. We'll see some of that in lesson 16. Great, so next thing I want to do is elaborate a bit more on this notion that we can choose the different parameterizations that best suit the context and the problem. In the particular case, for example, when we have a surface that's given in the form z equals a function of x and y, we can use x and y as the parameters. And as we talked about earlier, this would be a very natural parameterization for that type of surface. I've worked out here a little bit of what happens if you run through that choice of a parameterization in terms of the surface integral. Well, the derivative of r with respect to u, in this case u is x, would be just 1, 0, and partial derivative of x of g with respect to x. R sub v, well in this case v is y, so you run through that and you get 0, 1, g sub y. And once you actually calculate the cross products, here's what you get, and then take its norm and you get this. So again, remember here that I'm going back to z being g of xy. So that's why when you take the norm of this, you're going to end up with, for example, the square of the partial with respect to x. So that's what this is. Okay, so what's the point of doing all this? The point of doing all this is then we plop this into our area element ds. It was this times dA, and that generates this new expression for the scalar surface integral. So this is nice because in a lot of contexts, we've seen this in the course, the surface that we're studying, graphing, calculating something about has the form z equals some function of xy. In those instances, we don't have to do all of these prep work where we find the parameterization, calculate the derivatives, find the cross product, find its norm. We now have a nice formula to give us effectively the integrand of what it is that we need to integrate. It's the function expressed in terms of x, y, and z, written in terms of g of xy, multiplied by this square root term. This, again, should be a little familiar if you work through the line integral examples. This is exactly what pops up. And it, especially this part, 1 plus f prime squared, should be familiar from the arc length of a curve in the plane that has the formula y equals f of x. You might have covered that in Calc 2, but certainly you may have also run into it in the lesson on line integrals. So I want to show you then how you would use this alternative equation for the scalar surface integral. Again, this is an equation that started with the presumption that your surface was generated by an equation of the form z equals f of xy, effectively. So here's such an example. So let's look at the surface z equals x plus y squared. And I'm given the bounds here. Oh, and I think that this is a small typo here. So this first one should be the bound for x. So let's call it x, and I will fix that after the video. So I'm given the bounds for x and y, and I'm asked to calculate this scalar surface integral. Great, so at this point I say, hey, this is of the form z equals a function of x and y. I didn't want to use f, by the way, up here, because that's what we've been using for the integrand. So that might get a little confusing, so hence I'm using g. So g here is x plus y squared. And now I have a slightly different procedure. I don't want to start by parameterizing the surface. If I'm going to use all of this very nice work that we did, I can just jump straight to here. So I'm going to set up my double integral over the region D. And in fact, in this problem, I am given the region D. X goes from 0 to 1, y goes from 0 to 2. And then the function I'm integrating, y, I leave it by itself, right? Because y does not get altered. That was the point of this parameterization, to use x and y as the parameters. I don't have to change them in any way. So this stays unchanged. And then my ds area element becomes this. So I do have to calculate something here. I must calculate the partial of z with respect to x and the partial of z with respect to y. We'll do that over here. So I'm looking over here for z, and I do dz dx. That's just 1, because the derivative there is 0. And then I do dz dy, and that's just 2y, because the derivative here is 0. And then I'm going to take each one of these, and I'm going to square them. So inside the square root, I get 1 plus this one squared, plus this one squared. And then all of that is being integrated dA, which in this case is just x and y, so dx dy. Great. So that is how I've set up my integral. At this point, we can integrate this fairly in a straightforward manner. I'm just going to simplify things a little bit, and like I did before, talk about what you get when you try to think about integrating this. So this is another instance where I can split up this integral into a product of integrals that do not that each have just one variable in the integrand. So that's what I'm doing here. 2 plus 4y squared times over dy. Okay, so we've split this up here, and you can see that when I integrate from 0 to 1 in x, I just get 1. So really this reduces down to figuring out this particular integral. And this is an integral that you probably already know how to do, because we can use a u substitution. So we could let u be this. The derivative would be 8y dy, which contains a y dy. So which is, what is outside here after the u substitution. So this is an integral that, we've talked enough about at this point to relate it to something you should be comfortable with at this point, which is u substitution. So I'll let you fill in the details and verify that what you get is 13 root 2 divided by 3. Okay, so that was this example, and that's it for this video. Let me just double check. Yes, so that's it for this video. The one thing that I want to point out to just make sure that we leave the video having discussed the important highlights and elements is scalar surface integrals are just like surface area, what we did in the previous lesson, except that the integrand might not be 1. For an actual scalar surface integral, it's never 1. That's really the only difference. The other things that might pop in here are, for example, that as with surface area, you might have to decide which type of parameterizations to use for your surfaces, and you might have to decide to use specific parameters at some point to simplify your calculation. And then, keep this in mind. When the surface that you're trying to parameterize has the form z equals function of x and y, we've done the work here to relate, extract from the scalar surface integral an expression that's a little easier to work with when it comes to actually evaluating it. Okay, that's it for this video. I will see you in the next